Hello everybody. Today we're going to discuss the tensile testing lab for aerospace class AE2610 and its importance, the procedure, and how this relates to aerospace. So first of all, a little introduction. Imagine you're flying on a regular scheduled flight and all of a sudden the roof of the plane rips off. Terrifying, right? This is exactly what happened with Aloha Air Flight 243. Metal fatigue on this whole plane caused the fuselage to burst, the pressure vessel burst, and led to 65 injuries and 1 death. Now, the type of issue that happened here is extremely related to tensile testing, and these are the considerations that engineers have to take into account when they're designing vessels or even when they're maintaining them. So let's get started. First, there are two sections of this lab, the monatomic procedure and the cyclical procedure. The setup consists of a dog bone of aluminum, which is a little piece of aluminum, and we know the dimensions of it, and we know we're going to learn its stiffness. And we have an extensometer, which is this large machine here, and then we'll have a strain gauge. For this monatomic procedure, the dog bone is loaded into the extensometer here and here. It's put between, and it is slowly stretched out at a constant rate. Now this means the force is going to vary and the pressure inside, the stress and the strain of the material is going to vary as well. We measure the stress and the strain of the dog bone using this machine, and we also use a strain gauge, which is here. It's a small electrical transistor, to compare the results. So on the left you have the little extensometer, a small little thing. It measures the lengthening of the machine, or of the dog bone, sorry. And then you have several dog bones, and this is what it looks like after the test actually. And then you have the strain gauge, which is a little transistor that measures the changing of shape and the force inside the dog bone. After running this procedure, our takeaways show that the strain gauge actually is not accurate. It begins on a normal curve before getting erratic and going back to 0 elongation. And this is because we attach the strain gauge using adhesives, and the adhesives don't stretch, they break. So the strain gauge clearly is not as reliable. The extensometer gives us a very clear curve of stress and strain is exactly as we would expect, and using this we are able to find the Young's modulus as well as the yield stress and the point of fracture of the aluminum. This allows us to know how far we can stretch and pressure the aluminum without it breaking, how far we can do it where it will return to its original shape, that's the yield stress, and this is just important for structures and design to know how strong a material is. So next we did a cyclical study where we, same way, we loaded the dog bone into the machine, but we stretched it and then released the pressure, and then stretched it a little more and released the pressure, and then stretch it again, release the pressure one more time, and then stretch it until it breaks. This is called cyclical loading, and this very closely mimics the pressurization cycles, such as we see in the Aloha Air, or really any airplane fuselage. Any airplane is going to have these pressure cycles, and every time this happens, there's this thing called strain hardening that occurs, and we'll look into that in a little bit. And also it causes fatigue in the metal and eventually break, when that's what happened on the Aloha Air flight. So we load a new gauge in the machine, and then the machine is already pre-programmed actually to go through this procedure of stretching and releasing as we intend. So our data from this one are, again, our strain gauge didn't even show up this time. It broke right away, but our extensometer gives good data. Our graph, our stress strain curve here, shows the cycles where it is loaded before being released, and then loaded again, a little heavier, and then released, and then finally loaded one more time. A few important things to note is the slope of the curve for each release is the same. This is the Young's modulus. This is the amount of elongation in the rate of elongation for a material, and it will always be consistent as it is released and repressurized. And this is important to know for pressure vessels. It's also important to note that the strain does not return to 0. After each cycle, it increases slowly, because after each cycle, the metal is actually stretched. So even when the pressure is released, it still is longer than before. It's also important to look at the end here. It's not as smooth as the first test. As we can go back, you can see that this has a lot more bumps, and this is because the molecules inside the metal are being stretched and released, and they have to straighten themselves out because they're not being consistently pulled at a slower rate. It's also important to notice that the fracture point up here occurs at a higher level of stress and strain than for the monotonic test or the single test. This is because of the thing called strain hardening. We're repeating stretching and releasing a metal gauge like the one we have, the dog bone, will make it actually stronger. And this is a result of this happening here where the molecules will align themselves and form a stronger crystalline structure. So a lot of times aircraft metal, which we know is going to be subjected to cycles like this, is actually pre-hardened and it makes it stronger, but it also puts the default at this point here. So then after we do the pressure cycles, instead of returning to a different shape than what we desire, it's already fabricated to be at that type of stress or at that type of strain, so that after we load it up with pressure, it returns back to the original place. So if we compare the two tests, we'll see that when it was cyclically loaded, it became stronger, and this was the strain hardening where the molecules in the metal aligned and formed a more perfect crystalline structure. The monotonic loading, the sample was deformed elastically, or just stretched, and therefore it broke sooner. The strain gauge also failed early for both, which means, at least in this case, we used poor adhesives that weren't able to stretch the metal, and therefore it gave us very poor data. And the extensometer was a lot more reliable and gave us really clean data that is of the type that we desire. So the main takeaways is that tensile testing is extremely important in aerospace. This is because, obviously, of the case of Aloha Air, we have to know the effects of cyclical strain hardening and the effects that constant stress and release will have on an aircraft. This is because every single flight that a pressurized aircraft takes, it will be pressurized and released. And every time the metal is stretched out and then released back to its shape. And we really need to take note of that yield stress Young's modulus curve, because that gives us the expected amount of deformity that the metal is going to take. An extreme example of this is with the SR-71. While it wasn't due to pressure from an inside cabin, the metal frame of the aircraft actually stretched out because of the heat on the aircraft. So when the plane was on the ground, the fuel tanks actually just leaked fuel constantly. But then when it was flying and it was super hot, the metal would expand from the heat, and it would actually fit into place better. And therefore, the engineers had to calculate how much the metal would change shape, how much it would change size, how to assemble it in a way that the rivets would hold when it was both pressurized or heated and non-pressurized. This is also important for maintainers to remember, because they have to know how metal fatigues. Strain hardening does make the metal stronger, but also after several cycles, it becomes weak. You'll get cracks while the molecules will align themselves. They can also have the chance of breaking. It is also good to know that the cyclical test handled a lot more strain before breakage than the monotonic test. And this is also a great example of how in aerospace we will use strain hardening, where we will expand and compress metals that we know in our airframe so that they fit properly and they are stronger. It's also important to know that the strain on the aluminum did not return to its original size after each cycle of pressurizing and force in our test. In the Aloha Air, for example, this is what caused the incident. After many cycles, the metal was stretched out and repeated, and the molecules were aligning and realigning, and eventually they got stretched too far and they fractured. And while strain hardening does make the metal stronger, it also can make it more brittle, and therefore when you can get cracks easier, which is an important thing to note for maintainers in aerospace as well as engineers. Cyclical loading can quickly fatigue and damage materials, but single loading will damage them sooner, although there's very few cases where we're going to have single monotonic loading, and we really need to take note of the importance of cyclical loading. Hopefully this gave you a good insight into the lab for AE2611, its importance in aerospace, and some takeaways to note for when you're collecting your own data. Thanks.